work on some problems here. So just to do something kind of simple, we'll just do a bicep curl one. So if you're going to be, go ahead and give me a weight that someone's going to be trying to curl.
Like just any amount of weight?
Any amount of weight.
50.
Cool. 50, we'll go with pound dumbbells, not kilogram. That might be a little absurd. So let's go 50-pound dumbbell. Okay, that's definitely in the feasibility of thing. So go ahead and throw in the add notes so we can kind of work our way in through it. So we've got 50-pound dumbbell, which effectively means we're going to have about, so that would be, we'll say it's about, ends up being like a 23 kilogram dumbbell. Now, that's going to be obviously in their hand. So how long do we want to say the lever is from the elbow all the way to their actual hand where they're going to be holding it? "40 centimeters. Thank you, Zach. Sorry. The way the chat was overlapping, I couldn't see it. Perfect. Okay, the bicep insertion, we're just going to say we're going to figure, okay, so like if you feel in your biceps tendon, okay, and then you're kind of pushing down and you can kind of feel that it's only going to be attaching right about here, and there's my elbow joint. So we're talking about maybe an inch or so. So we're going to go and say that insertion is about 3 centimeters. Okay. Now, the other thing we've got is the center of mass of the forearm and hand is going to be located, instead of that 40 centimeters, it's going to be closer to only about 45% of the arm. So we're going to be looking at about 18 centimeters down. And how beefy do we want to say the weight of their forearm and hand is? How heavy do you want to say their forearm and hand is? Some pretty skinny forearms for someone that's curling a 50-pound dumbbell, but fair enough. Let's go ahead and go with it. So we're going to say that's going to be about 2.5 pounds. So it's going to end up, I'll round up just to make it easier. It's going to be a 1.2 kilogram mass. Okay, so if we know the effort times the effort arm equals the resistance times the resistance arm, we're going to be able to solve for the bicep force equals, well, what? So how are we going to set that up, guys? How are we going to organize that? So we've got the effort times the effort arm. We don't know what the effort is, but we know the effort arm. We're multiplying that by 3 centimeters. Okay. Now, nothing we have is in newtons right now, but we're going to go ahead and we're going to put in that conversion. So we're going to have the first part of the resistance is just going to be the internal resistance, which is the weight of the actual forearm and hand. So we're going to have 1.2 times 9.81, and then multiplying that by the distance to the center of mass, which is going to be 18. Okay? Now, we're also going to say plus now that 23 kilograms times 9.81, and then multiplying that by 40 centimeters. So if we think about bracketing this, so we run this individually, if we then divide both sides by 3 centimeters, we're left with the final equation of our biceps force equals the mass of the forearm and hand multiplied by gravity multiplied by that center of mass position from the lever, from the actual fulcrum, and then plus the mass of the dumbbell multiplied by gravity and multiplied by the length of the lever arm. So that's how we can effectively solve for the force required just to hold that in position, just to hold that right where it's at. Does that make sense to you guys? Makes sense to one person. Cool. All right. So now let's go ahead and work our way through another problem, but we're going to apply the same basic concept. Does that make sense to you guys? Okay. So let's talk through the exercise known as a bodyweight hamstring curl, okay? Now, when we say a bodyweight hamstring curl, effectively what you're going to have is someone who's kneeling on the ground, okay? Arms at their side, and they're going to use just their hamstrings to control themselves all the way down and then trying to lift themselves back up. No, they didn't suddenly get taller. I'm just very bad at scale. Okay? So we've got two different things. At the top, we don't have a lot of force because remember, our force is always going to be that perpendicular to the angle of pull. So we really have, if we were going to draw a triangle out, since we're slightly in an angle, we've got very little force that we actually have to produce to keep ourselves from falling forward. Okay? So we're trying to figure out how much force are the hamstrings going to have to produce when you happen to be about flat with the ground. Okay? So what you need to figure out now is, okay, how much do you weigh? Figure that out in kilos, so take your weight in pounds divided by 2.2. From there, we figure that we're going to be lifting probably about 88%, sorry, this marker's already going bad. 88% of your body mass, and your center of mass here, we'll just say it's going to be at 50% of your height. When you subtract an initial, we'll say it's only 15% when we subtract the shin and the foot. Okay? Now the hamstrings itself, they're only going to insert probably that same type of, where we're going to find the effort arm is only going to be, we'll say, it's a grand 4 centimeters. So you're going to be able to solve for your resistance and your resistance arm. So what we're looking for is the effort. How much force would you actually have to produce in order to go ahead and lift yourself up. I'm going to go find a better marker, and then I'm going to pull up a video example of what I'm talking about. How are we doing figuring out the math problem there, guys? That's okay. That's okay. It's meant to be difficult. So this is, gosh, this is probably like from a little over 3 or 4 years ago. This is at my friend's gym back in St. Louis, and this is post shoulder surgery, so I am really weak. But the basic idea is your partner holds you down. You try to control yourself down with just using your hamstrings. I break really bad with my hips, and then you pull yourself back up. So you have that lever arm, and then try to pull back through. So that's what we're effectively looking at. Okay. So in this example, okay, I weigh about 95 kilos. So I would take that 95 kilos and I would multiply that by a grand total of 88%. So effectively what I'm taking out is 9.5 and another, wait, yeah. So another 2. So really we'll just drop 11.5 out to make the math easy. So effectively my resistance is going to be equal to about 83.5. I would then multiply that by gravity of 9.81 meters per second squared. So then I got to figure out the length of my resistance arm. Now my resistance arm is going to be initially taking 15% off my height and then multiplying that by 0.5. So I am not tall. I am closer, I'm 5'10" if I don't lift weights, actually closer to 5'11", which is kind of weird, but I'm usually like 5'9" and some change. So, and that's due to spinal compression. That's relatively normal when it comes to a lot of lifting. So that means if I'm usually about 5'9", 1 inch is 2.54 centimeters. It puts me at like 170. So if we just take 70 multiplied by 2.54, so that's 140 plus 35. So it'd be 175. Yeah, I'll just say I'm about 175 centimeters tall. So I take that 175 centimeters or 1.75 meters and subtract 15% of that. 15% of 175 is going to be 17.5 plus an additional 8.75. So that's going to give me 26.25. So take that initial 175 minus 26.5. And that's going to give me a sum initially that I'm going to come over and use of 148 point, actually it should be 25, but I'll round up just because it makes life easy. So we take 50% of 148.75. So we're going to be left with 74.25 centimeters. Okay. Now on the other side, we know for a fact that's going to be 4 centimeters, and we're still trying to figure out what the heck is our effort. So then we're going to go ahead and divide both sides by 4 centimeters. And then that's going to give us the total amount of torque required for me to lift myself in that position. So your classmate Zach has seen me do it recently, so I still got it. Boy, howdy, it'd be a lot easier if I wasn't so heavy. But you look at the amount of force that's actually required to do that. So I think you end up with, yeah, that's definitely calculator time. I'm not doing that in my head today. I'm being lazy. So nice thing is, these things have calculators in them, so I'm just going to pull it up and do it that way. And if you guys come up with an answer, go ahead and share what you came up with.
What's that last number? Is it 74.25?
Yeah, 74.25, because that's that 50% of my height is where we're going to find that center of mass.
Gotcha.
Mm-hmm. All right, so 83.5 times 9.81 times 74.25. 4.25 equals divided by 4. So I come up with a nice and small 15,205.19 newtons of force between the hamstrings there, which is awesome. And that's just so I can hold myself in a position. So I actually have to produce more than that. And so if we want to convert that into kilograms, we're going to just go ahead and divide that value by 9.81. So you guys can think about it. So it's just a really small 1,549.9 kgs of force, or we want to convert that into American and get that into pounds. We're going to now multiply it by 2.2, which is literally going to give you 3,409 pounds of force. That's how you trade in your hamstrings and you get yourself some pork cords. How are we doing on your own, guys? How are we doing on your own? Nice. What was the number you got up? You got, Rollin? Did you run your own numbers, like based upon your own height, your own weight and everything? Or you just copy over mine?
Oh, I just did yours, my fault.
No, it's okay. It's okay. So that's the idea, is we're going to try to make it relative to yourself.
Okay.
So
I got 6,914.8 kilograms, but I do not think that's right.
you're in the ballpark, Zach, depending on height and everything else. You could be,
Yeah, like
your number.
set it up like 83.54 times 9.8.
Yeah, I think if anything, your number should be really similar to mine, since obviously our weight is pretty similar, and so is our height. Obviously, if you're larger than I am, we expect your numbers to be bigger, and if you're smaller, then we expect your numbers to be smaller. So yeah, that's okay. So, do you guys want me to work my way through this, like walk through this again, or do you guys like to move on and try this with a different exercise?
Walk through it one more time.
Okay. So, when in doubt, guys, that's why we start off with this diagram. I figure out like how much force we're going to have. So we figure in the very bottom, okay, that's where you're going to have to produce the greatest amount of force, because that's where we're going to find that perpendicular to the lever arm force is going to be the longest, okay? Because we've got everything displaced the furthest from. Now, our hamstrings are going to insert into our tibia, so it's effectively on the one side. No matter what we do, that's where the force is going to be being produced, okay? Now, as far as our mass of our body, the center of mass is what we're entering in here, okay? Now, if you wanted to, you could literally figure out the distance that your head is from the center of mass, the distance your shoulders are, the distance the center of mass of your torso is, the distance the center of mass of your hips are, the distance the center of the mass of your thighs are, and add all those together. And that would give you the same effect of what we summed up over here by just doing it all as one big average. Okay, unfortunately, that's what you do have to do when you move around. Luke, that's okay. That's okay. It's not too far off. Okay, so when we're trying to figure out that center of mass. So now we're looking at the lever arm, okay? Well, first and foremost, typically 12% of your body weight is effectively in your shins and your feet, between both of them. So it's 6% each. So hence why you're only lifting 88% of your body mass whenever you do this. Then what you're going to go ahead and do is you're going to be lifting, or figure the center mass is about 50% of your remaining height, and 15% of your height in this example, for what we're giving you guys, is coming from effectively your feet to your shin, or to your knee effectively. It's 15% of your height. And depending on how you're built, it might be a bigger number, probably is actually a bigger number, but I was just throwing out a number there. Now, of that remainder, we figure your center of mass can be 50% of your height. So effectively from the knee up, 50% of that distance is where we're going to see your actual center of mass. Now that is another assumption we're making, which is going to be different. So if you're like a total bro at the rec that only has muscle in the upper body and nothing in the legs, you might see that instead of being 50% of height, it's closer to maybe say 60, 70. If you're somebody that, you believe in, occupy squat rack and you don't really care about mere muscles, it turns out you're probably going to be lighter in the upper body, heavier in the lower body, so that center mass might be less than 50% of that remainder. So what you're going to do, you're going to take your height, multiply it by 0.85, because we're only taking 85% of the height because we're subtracting 15. Then we're going to go ahead and multiply that number by 0.5. And that's going to give us that center of mass of where we're thinking it's going to be on the remainder. Now from there, we've got everything we need, because we have your mass, not including the lower leg, which isn't involved in this formula. We have your lever arm for the resistance, because where that center of mass is going to occur. And then we're going to go ahead and have, I just saying that everyone's hamstrings insert 4 centimeters down, where you would have variability there. But that was, once again, kind of a stand-in number. Does that make a little bit more sense there, Cass? Awesome. So this is where we can figure out effectively, what percentage or how much force we have to produce. Because a lot of bodyweight exercises, people might poo-poo them and say that they're too easy, to which I simply say, go ahead and do a handstand push-up. And if you can do a handstand push-up and you're so hardcore, then do it with one hand. And so I've never seen anybody do that. I'm sure there's probably somebody on YouTube that's done it before. And if they have, that is either incredibly small and light human, or that is a terrifyingly strong person who can literally put themselves up in one hand, lower themselves down, and push themselves back up. And so, yes, exactly. It's kind of like when you tell them to do a one-arm push or pull-up, and then they grab onto the bar and they put their other hand on the wrist, like, no. One arm, that's it. That's all you get. And all of a sudden, no, I can't do that. I'm like, yeah, you can, because it's really hard. So now we're just looking at single joints, because single joints are going to make this a lot easier whenever we're initially breaking this down. Okay, so now instead of everyone at least has an idea of a number here, right? Of a good idea of how much force they're producing. So let's go ahead and we're going to get on a leg curl machine. Okay, so you're going to go ahead and get yourself on a leg curl. So I'm just going to leave the final force here because we're going to do a little comparison, okay? So we're going to draw it out. And in the leg curl, we're going to say it's a laying leg curl. So you're laying down on the pad. Pad goes against the back of your legs and you're trying to, lift it upwards, okay? Here's your head and you're smiling because you're laying down. That's comfortable. You're doing the leg curl, okay? Now, remember before when we said that length here was 12%? Well, now that is going to be we're still solving for our effort, multiplied by our effort arm, which again is just going to be 4 centimeters because we're pulling from right there, 4 centimeters below the knee, equals Now we're going to have the resistance, which is going to be the weight we're actually curling, times the resistance arm, which remember guys, that's going to be 12% of your height. Okay. No, that's dumb. I said 85% of your height was the rest of it. So it's going to be 15% of your height. Okay. Plus the resistance of your lower leg. And remember, your lower leg that's the 12% of your body weight when you're looking at the weight of your shins and the weight of your feet. If you've got just some massive calves, it could be obviously higher than 12%. If you got little toothpicks, it's going to be a smaller number. So we're going to figure this right here is going to be 12% of your body weight. And then we're going to be multiplying that by the resistance arm, which we're going to figure the center of mass because your foot's all the way over here. We're just going to say that's going to be at effectively 50% of the 15% of your height. So we're going to say that 15% now is going to be in half. We're going to find that center of mass at 7.5% of your total height. Okay. And the resistance. How much weight do we want to say we're using on the leg curl?
100 pounds.
100 pounds. Fair enough. 100 pounds is going to be equivalent to about 45 kilograms. So 100 pounds, or what you guys are really going to answer is 45 kg. And remember, because we need to get these forces into newtons, so we got to multiply by gravity. So now, given this formula, what are you guys coming up with as far as the loads, the forces your body has to come up with?
With the resistance arm, my computer kind of broke in and out. Did you say that we're taking 15% and then making that 50% of the 15%?
Yes. Yes.
Okay, gotcha.
Yeah. Since, if you think about the way that your lower leg is built, you're going to have, your calf, your gastroc and soleus sitting up higher. But then you still have your foot, which is pretty dense because it's mostly just bones and, some muscle and connective tissue. So we're just going to say that center mass is going to be halfway through it.
Gotcha.
Mm-hmm. So go ahead and throw up into the chat the numbers that you guys find. And in the interim, I'm going to go ahead and solve for my own numbers. So you guys have that and we can kind of do a little fun comparison. Nice, Luke. I came up with 3,263.95 newtons for my initial amount of force. Now, dividing that by 9.81 is going to give me a grand total of 332 kg, or we're going to convert that into American. And we're going to end up with a grand total of 731.9 pounds of force. So, yeah, Zach, you maybe messed up your order of operations somewhere in there. Luke, depending on obviously how tall you are, because a longer lever equals you're going to have to do more work. All those are going to definitely change the effective amount of torque you're needing to produce.
Are you using 9.81 in this one as well?
Yeah, because we're always doing this under the effects of gravity.
I couldn't hear you. I'm sorry.
Yes, because we always have the effects of gravity.
Got you.
Because that's how we get it into newtons. And so
I was going to say that. Sorry to interrupt. I had a question. So, like, whenever you calculate the resistance, you're multiplying the weight that you're using by 9.81, and then
yeah, you're always going to be multiplying those resistances.
Height. Okay, and then you add 12% of your body weight times 9.81 again, multiplied by that same percentage of your height.
Okay, now it's actually going to be half of that percentage. So that's why we're doing it by 7.5% or 0.075. As opposed to when we're looking at what the resistance you're actually lifting through the pad, that's going to be 15% of your height. So your height times 0.15.
Okay, that makes more sense. I was just confused about which percentage of height to use where. Okay, thanks.
Yeah, guys, it's okay. That's why we work through examples and we talk our way through it as we're doing it. Okay, I'm going to wait until I see you guys either throw up your numbers in the chat or go ahead and just say yes in the poll and that you guys are ready to move forward. Oh boy. Okay, so those of you guys that haven't hit the yes button on the poll yet, what would you guys like me to go ahead and go through again? Or these are the people that logged in and then immediately walked away. So that way it would count that they were here for roll. So just think of it this way, guys. If you want me to go ahead and just subtract, 5 points from your grade, don't hit anything on the poll right now. If you guys want me to subtract points, so don't say yes on the polling, or put anything up in the chat, or unmute yourself and say something. You guys think I should do that? I think I should just maybe take a couple points off since they're not really here, guys? Or is that not fair? For those of you that actually are here. I'm not going to do it. I don't know. I was hoping I was going to get him to do something. But. Okay. Now, aside from making you guys think through things in ways that you're not used to, what do you guys think is the big take home here? Like, why do we care? Why should we do things like this?
To kind of figure out like how much force you can produce during like a hamstring curl or like a bodyweight ham, or maybe like if you want to do an upper arm and bench press.
Yeah, or you can do it with squatting, you can do it with running, you can do it with jumping. So this gives us some good information, which is how much force are we really encountering? Like really, how hard do we have to contract in order to get ourselves to go ahead and move? And the other thing about this, guys, is this is just being able to hold a position. So we're gonna do one where we try and move in a second. We're gonna do a vertical jump, and we're only gonna go through the calves, which is probably gonna be the easiest way to go about it. Now, here's the thing. What is one of the major stimuli that drive muscle growth over time when it comes to a training variable? So when it comes to building muscle, when it comes to trying to make your muscle stronger, there's a number of things that help that along. One of the major components is going to be literally the total amount of tension you have to produce. So if you had to pick between doing a hamstring curl or doing the bodyweight hams, which of those two is actually going to be more productive because we're having to produce a greater amount of force?
I don't know what the first option you said was, but I'm going to say bodyweight hams because I feel like you got to there's a lot of resistance there.
Now, don't get me wrong, some people aren't ready for it. They're not strong enough, so they really should be doing a hamstring machine type exercise and building up to the point at which they can try and do it. But the basic idea when it comes to building muscle, one of the major components is literally the tension that muscle has to produce. So between the bodyweight ham and the laying leg curl, the bodyweight hamstring makes you produce a lot more force. So that's going to cause more damage to your muscle tissue, which in theory, if you're ready for it, is going to be more productive as a form of training your hamstrings than doing a laying leg curl. Now, the other is the total amount of volume work you do. So AKA how many total sets and reps, and that's when we talk about work in the physics sense. Now, it turns out most people are gonna be able to do a lot more work on a leg curl than they can on a bodyweight ham. That's why just because we can do something that's super high intensity doesn't mean it's a good training method, because we can't do a lot of work like that before we get tired. But all we're doing anytime we're lifting weights, we're just doing biomechanics. We're just trying to figure out like how much force are we actually producing. So let's go ahead and figure out how much force we're actually producing through our calves when we're going to be jumping off of the ground. And this is where things are maybe going to get a little Fruit Loops for a few minutes, and that's okay, guys. It's okay. This stuff is not easy, but it's going to help you guys more thoroughly understand how the body works and how we're actually able to move ourselves. So let's erase all of this nonsense and let us start. So your goal is going to be to jump off the ground and to jump high at that. So we're going to have our person on the ground, and we're going to look at the force through the ankle when you're trying to jump off the floor. Okay? So we're going to say when you're really doing a true maximal jump, you're trying to go ahead and get yourself to plantar flex at, we'll say what ends up being about 180 degrees per second. Okay? So this is all going to make sense in a few, but give me a moment, okay? We're trying to go up to 180 degrees per second. That's our final. Our initial equals 0 degrees per second because we're obviously just standing there on the ground. Okay? Now we're going to do this acceleration from this lowest to this fastest. We're going to say it's going to take us 0.2 seconds to get the change in time. Okay? So from here, we can figure out, okay, what's our acceleration? Now, let's think about what's going on with these levers. So you're actually rotating around your ankle, and it's the ball of your foot that's pushing into the ground. Now, at the ankle here, you're lifting your entire body weight minus your feet. And so you're going to be lifting effectively. What's going to end up being, we'll say it's a good 95% of your body weight. That's probably wrong. Now, I've got really big feet, especially for how tall I'm not. Not that any of you guys care, but I literally wear size 13s, and I am, like I said, 5'10" on a really good day. So I've got freaking flippers. So I probably actually have a little bit more of my body weight in my feet than your average person just because they're like a hobbit. Whereas if you happen to have really small feet for how tall you are, you're going to see this percentage be higher. These are just stand-ins. We can use this for our math, okay? Now, this lever arm, well, that's equal to how long your foot is. Sorry, Cass. Let me switch up markers and see if another one can give us a bit better. So the length of this lever arm here, we're going to say that's going to be, well, really, take your shoe size and then just go ahead and just multiply that by 2. And we'll say that's going to be the length of the lever arm. The reason I say 2 is because I know I'm making a mistake. The key is, the reason I say multiply it by 2 is because we're going to be pushing through the ball of our feet, not the actual on our toes. So it's not the full length of our foot. And your shoe size tends to correlate in American pretty closely to how long your foot is in inches. Kind of closely. Not perfectly, obviously, okay? So that's going to be the lever arm. Now, sorry. This is going to be the resistance. This is going to be the resistance arm. Now, the actual effort arm is going to be that same shoe size, but now we're going to be multiplying it by 2.05 because our gastroc and soleus actually attach a little bit further back from the center of mass going through our ankle. So it actually has a slight leverage advantage. So now I need to go ahead and pull up a happy little equation slide because it's going to get crazy but fun. Well, I guess fun's relative. I'm having a good time. I don't know if everybody else is having a good time. And I appreciate those of you guys that are putting up things both in the chat and unmuting yourself and talking with me, because it definitely makes this a lot more enjoyable. Yeah, no worries. Both okay, so you are lifting a grand total of 95% of your body weight. The effort arm is your shoe size times 2. Sorry, your effort arm is your shoe size times 2.1. Your resistance arm is your shoe size times 2. So that way you can actually figure out, okay, this is how much we need to overcome. Okay. Now, here's what's really cool, is notice that formula in the upper right, where torque equals your inertia, which is gonna be your mass, multiplied by your radius squared times your acceleration. So in order to just push yourself up, that's the first part we're going to solve for. So we're looking for balancing this equation. We're going to have R times RA equals EA times our effort, which we don't know what that is. So we're going to go ahead and take, once we multiply these two together, divided by the effort arm, that's going to equal our effort. That's just to go ahead and hold yourself in a position, but we want to move. So here's where we're going to have some fun in a moment. But when you guys come up with what you think is your answer for your effort, go ahead and put that up in the chat.
Did you say what our resistance is, or are we figuring that out?
Yeah, so your resistance is that 95%
Nine.
body weight.
Okay, got you.
Mm-hmm. We're doing this kind of in a, for lack of a better term, a quick and dirty methodology, so that way we can get through it and have you guys understand. What type of dog you got, Catherine?
She's a border collie. She's really old. She's almost 12.
Nice.
She likes attention, and every time she hears someone talk, she jumps right on my computer.
Wonderful liabilities of having pets.
Yes.
The reason why I lecture from on campus and not from my house, because our cats are friendly, but one of them she's super friendly, but she likes to always get attention from me if I'm around. And so if I'm standing like this, she likes to face me standing on my desk. So guess what? You guys get a nice video of.
That's why I don't ever turn my video on, because you would just see her and not anything else.
Oh no, I'm okay with seeing a dog. I just don't think any of you guys want to wake up to as my wife and I refer to it, of staring into the eye of Mordor, because you're literally just going to have cat butt in your face. And that, and honestly, aside from the weird little took it a couple minutes to hook up this morning. The internet here is on campus is really reliable. So keep that in mind, guys, whenever you're taking the exams and otherwise. There's nothing wrong with taking them at home, obviously, if that's what works. And if you guys know you've got good, reliable internet. But if you are able to, I would suggest when you're doing some of those exams of trying to go take them in the library or otherwise on campus, or like maybe have like a phone that can hotspot or something else, like just a contingency, since the wife and I, we use Windstream up in Lexington, and it definitely has its issues on occasion. So, and I don't want you guys to miss points just because, you know, your internet failed you. So, what are you guys coming up with for your numbers? Go and throw that up in the chat.
If we did our weight in kilos, do we have to convert our final number into kilos too?
Okay, so if you did your weight in kilos, then you don't have any of these numbers in newtons. So the numbers you're going to be solving for is going to be your weight in kilos. So for the true newtons, you need to be able to multiply that by a bit more. Now, okay. John, that number looks a little small. And same thing, Zaria, but that's quite possible. So if I was to go ahead and take my numbers, so I would initially take 95 times 0.95 and then multiply that by 9.81, multiply that by 26, and then divided by what will end up being, or just divide that by, yeah, so I came up with 863.75.
Are we supposed to multiply the resistance value we get by the resistance arm?
Mm-hmm.
Okay, that's where I messed
Remember,
up.
guys, you still end up with the basic formula of effort, which is what we're trying to solve for, times the effort arm equals our resistance times our resistance arm. And yes, so it's 95%, and you still need to incorporate gravity up here. So for me, this comes up with 863.75 newtons of force. There we go. Cass, that looks right. John, that looks right. Good. So, I mean, the simple thing is, the cool thing is, and that's part of the reason why most people's calves are so small compared to when you look at literally their thighs and their glutes above it, because you've got really good mechanical advantage through your foot. Like, that's actually the only spot in your body where your leverage is actually better than effectively what your body resistance is going to give you. So yeah, those numbers, now that makes sense, guys, because turns out if I outweigh you, then the amount of force that I produce should be heavier than yours, simply because I've got to lift more weight than you, and that's okay. So, all right. Keep throwing the answers that you guys have got up into the chat so we can effectively see what you guys came up with, and then we're going to really have some fun because we're going to figure out how much torque it would take to effectively do a really aggressive ankle hop. So going from 0 degrees per second to 100 degrees per second in 0.2 seconds. So the first thing that we're going to go ahead and I'm going to try and change the lighting, see if that helps so you guys can see this. I'll be right back. That didn't really help, did it? Luke, Haley, those numbers look good. Does that make the numbers a little bit easier to read? Probably also help if my handwriting wasn't what's colloquially referred to as garbage. Okay. So now we're going to have ourselves a little bit of fun, and that we're going to figure out that torque it's going to require to get you to go up to the certain speed. So we know our initial is 0 and our final is 180. That means we're changing 180 degrees in 0.2 seconds. So our acceleration here is going to equal 180 divided by 0.2. So we're going to have effectively degrees per second squared. Right? Now, our inertia, well, the radius, that is going to go ahead and be that wonderful shoe size times 2. And so then we're going to have to square it. And the mass, well, that is going to be this resistance up here. So notice that's just the weight of your body. You don't have to incorporate gravity. So when you put all those together, guys, now let's figure out what type of torque you end up with.
Could we go over the torque formula one more time?
Yeah, no worries, bud.
Awesome.
So our total torque that we're going to have to produce is going to be equal to our inertia. And the rotational inertia is going to equal the mass multiplied by the radius squared. And so the mass is going to be that 95% of your body weight. We do not incorporate gravity, okay? Because we're doing this independent. This is just the torque we need to produce to make this movement be so aggressive and quick. Then our radius is going to be that shoe size times 2. So that's going to go ahead and give us what's going to end up being our inertia.
Gotcha.
Now, the key thing to keep in mind, guys, is with our radius now, since it's not relative to the other, we have to get this into true meters. So instead of a shoe size times 2, guys, it's going to be shoe size times what's going to effectively be point. Yeah. It's going to be more like should be 0.2. So I messed up my numbers. I'll fix them real fast. This is going to be big, but it ain't going to be that big. So then we go ahead, we multiply that by 900, and then we get a nice small total amount of torque required in the case of me trying to accelerate my body that quickly through my feet of 2,000 or 200,000 and 11,185 Newton meters. Just a little powerful. Just a decent amount of torque. And if the numbers look absurd, it's because they are. Yes, yeah, because that's going to be your change in degrees per second. It's going to be 900. Because what we have is we have an initial velocity or rotational velocity of 0, a final of 180 degrees per second, and we get up to that velocity in 0.2 of a second. So you take 180 degrees per second divided by 0.2 seconds. Now we get the actual change, which is going to effectively be that acceleration, which is going to be 900 degrees per second, which is crazy fast.
Did you say the units will be in Newton meters?
Yeah, the final equation, we're going to get those values are going to be in Newton meters.
Okay.
Because that's going to be the torque required. And hence the torque we come up with is just Fruit Loops massive. Like you're not going to come across something like that. But yeah, Rollin, that looks about right. Nice. Same thing, Zach.
Two, 3, 238.
Luke, you're currently unmuted if you're not aware.
Sorry about that. I'm
You're
muted.
good, man. You're good. So we've done some more rotational physics formulas. I guess you could say the homework I want you guys to do is start looking at your joints and how much force or how much torque you're having to produce, how much force is actually being produced by the muscles whenever you happen to be doing the actual task that you guys are doing for your project. So go ahead and try to work on that math on your own. And then whenever we meet on Thursday, our goal is going to be to put you guys in groups so you guys can all effectively talk amongst yourselves and work on trying to understand the math side of the rotation of what's going on with your joints in your groups. So you guys are still going to all be working together, thinking about what's the weight of that segment. And okay, so then what's the weight of all the other things that's being lifted above and below? And I'll help you guys obviously work on setting this up, jump in each different group, and we'll be able to go through from there. But do you guys have any other questions before we go ahead and call it a day today? All right, well, since that's pretty quiet,